everyone, in this video we'll be discussing ECG signal analysis using Fourier and wavelet functions in the context of signals, networks and systems. This project was made by Group 11, that's Rishikesh, Vikrant, and Neel. The electrocardiogram or ECG records the electrical activity of the heart over time. It's one of the most important tools in detecting abnormalities in heart rhythm and stress-related conditions. From an SNS perspective, the ECG can be treated as a biomedical signal that passes through system, and we can analyze it mathematically using transformations like the Fourier transform and the wavelet transform. Our objective in this project is to understand the ECG signal behavior through these two analysis methods. The ECG is a continuous time analog and non-stationary signal, meaning its frequency content changes with time. It mainly consists of three parts: the P wave, representing atrial depolarization, the QRS complex, which shows ventricular depolarization, that's the main spike you usually see in ECG graphs, and the T wave, showing ventricular repolarization. The typical range of ECG signals is between 0.05 to 100 Hz. In the signals and systems framework, we can model ECG as an input signal x of t passing through an LTI system. By doing this, we can apply concepts like filtering, for example using low-pass filter to remove high-frequency noise or a notch filter to eliminate power line interference. The ECG can also be expressed as a sum of sinusoids using the Fourier series, which helps us analyze its frequency components. This slide shows a basic block diagram of an ECG system, starting from signal acquisition through amplification, filtering, and finally the display or digital processing stage. Each block plays an important role in the conditioning the raw signal for analysis. The Fourier transform converts a time domain signal into its frequency domain representation. This is useful for identifying periodic components, designing filters, and analyzing heart rate variability. However, one major limitation is that the Fourier transform doesn't show when those frequency changes happen, which means it isn't great for analyzing transient or time-varying events in the ECG. When we apply Fourier analysis to ECG data, we can see how different frequency bands correspond to different physiological features. Low frequencies represent baseline drift. Mid-range frequencies contain the main ECG waveform. High frequency are mostly noise. Using the fast Fourier transform, we can efficiently perform this conversion digitally. This helps in designing filters, extracting features, and even analyzing heart rate variability. For example, high power in the 0.04 to 0.15 range indicates stronger sympathetic nervous activity. Wavelet transform theory. While the Fourier transform only gives frequency information, the wavelet transform gives you both time and frequency information at once. It works by decomposing the signal into smaller wavelengths, which are scaled and shifted version of a base or a mother wavelet. Common types include Haar, Debauchees, and Koiflet wavelets. Wavelets are perfect for non-stationary signals like ECG because they can detect transient features such as sudden spike or arrhythmias. In wavelet analysis, the ECG signal is broken down into multiple levels. The higher levels capture fast changes, the mid-level represent P and T waves, and the lower level corresponds to the baseline drift. This method is very effective for denoising feature extraction and arrhythmia detection. This slide shows a brief code snippet from a machine learning model that we used to test automated ECG analysis. By combining Fourier and wavelet based features, such models can classify or predict abnormalities more accurately. To conclude, ECG is a rich, non-stationary biomedical signal that benefits greatly from analysis through signals and systems concepts. The Fourier transform provides frequency domain insights and helps in filter design, while the wavelet transform adds time frequency detail and detects transient patterns. Together, they allow for a much more accurate interpretation of ECG signals and are valuable in clinical diagnostics. Thank you.